Have you ever stopped to think, with all the amazing things AI can do now, why does it still feel like something's missing? Like that basic common sense or real flexibility, that gut feeling we have. It's a really big question.
It absolutely is. There's this gap, isn't there?
Exactly. And today we're going to dive deep into something that might just be starting to bridge that gap. It's a new AI model called the Continuous Thought Machine, or CTM. It comes from researchers at Sakana AI, Tsukuba University, and the IT University of Copenhagen.
A really interesting collaboration.
Right. So our mission today is to unpack what makes the CTM tick, how it's inspired by, actual brain activity, the timing aspect. We'll look at the surprising things it can do, and crucially, what this could all mean for where AI is heading. It's really about how this thing thinks.
Or processes information, in a way that seems much closer to biology.
Okay, so let's start there. The gap. If we strip away the jargon, what's the fundamental difference between today's AI and, say, our brains? Current deep learning. It's powerful, no doubt.
Oh, absolutely.
But it simplifies things, right? Especially neural activity.
Yeah.
It sort of throws out the timing, the rhythm, like turning a complex firing pattern into just on or off.
That's a great analogy. It's like losing the music and just keeping the notes.
Yeah. So what are we losing? What's missing that explains why AI struggles with, flexibility, learning from less data, common sense, generalizing properly?
Well, that hits the nail on the head. Evolution gave biological brains these incredibly rich dynamics. Think spike timing, these waves of activity, oscillations. Our current AI, it prioritizes efficiency, which is understandable computationally, but it means we've largely ignored these temporal dynamics.
Okay.
And if you think about it, our own intelligence, human intelligence, is completely wrapped up in time. The flow of thought, memory, prediction.
Right, the arrow of time, as they say.
Exactly.
Yeah.
The CTM researchers argue pretty forcefully that time needs to be central to AI design if we wanted to approach biological intelligence. They literally say we're facing a strong limitation by ignoring neural activity as core to intelligence.
Okay, so they've identified the problem, the lack of real timing, of dynamics. How does the CTM actually try to fix that? What are the core ideas they're putting forward?
This is where it gets really fascinating. They introduced two main innovations. First, neuron-level temporal processing.
Okay, what does that mean exactly?
It means instead of a simple activation function like, say, RILU, where a neuron just reacts instantly.
Right, the standard thing.
Yeah. Here, each neuron has its own unique weights to process a history of the signals coming in. So each neuron has its own little private model considering the past.
Whoa, okay, so each neuron has memory, in a sense.
In a way, yes. It considers the temporal context. And the second big idea is using neural synchronization as the latent representation.
Latent representation. That's like the AI's internal thought or understanding.
Precisely. But instead of just taking a snapshot of which neurons are on at what moment.
Which is what most models do.
Right. The CTM looks at the synchronized activity between neurons over time. It's about how they fire together, how they resonate. That pattern of synchrony is the representation.
That sounds fundamentally different. Neurons with history and using their collective rhythm as the meaning. What does that actually let the CTM do internally?
Well, it is a fundamentally new kind of representation. They're tapping into the exact timing and interplay of neurons. This creates what they call an internal thought dimension.
A thought dimension.
Yeah, it allows the CTM to build up and refine its understanding step by step. Even if the input is static, like an image, the CTM can kind of mull it over internally. This internal process unfolds internally. It's not tied directly to the input dimensions. It creates its own timeline of internal thought steps.
Like it's thinking about the image over time.
Kind of. If you look at visualizations, the neurons aren't just on or off. They show these complex, multi-scale dynamic patterns, always shifting, evolving. It really aligns with this idea that these dynamics are probably a cornerstone of intelligent thought.
That makes a lot of sense. It sounds much more alive in a way.
Yeah.
Now, you mentioned something really intriguing that comes out of this design, adaptive compute. What's that about?
Yeah, this was one of the really surprising emergent benefits. It means the CTM can basically decide how much thinking or how many of those internal ticks it needs for a given problem.
So did it just run for a fixed amount of time?
No. For easier inputs, I reach a confident answer quickly and just stop earlier, save computation.
Okay.
But for harder inputs, it can keep computing, run through more internal ticks to try and figure it out.
How does it know? Usually you need complicated extra mechanisms to get AI to do that, right?
Yeah.
Stuff that's hard to tune.
That's the amazing part. The paper says it just falls out of the CTM as a consequence of the core design. It inherently links computational effort to difficulty.
Wow.
Which, from a biological standpoint, is really gratifying, as they put it. Our brains don't use maximum power for every single thought.
Right, that would be exhausting. So it's efficient in a smarter way. Okay, beyond efficiency, let's talk about reasoning. They tested this on mazes.
Yes, a challenging 2D maze task. Given a start, an end, find the path. But crucially, they didn't give it standard positional information.
So no easy clues about where things are. It had to build its own map.
Exactly. It had to build an internal representation of the maze's space. And the results. It far surpassed the best baselines, like LSTMs, and it was much easier to train.
Impressive. How did it seem to solve it?
The researchers suggest it had to sort of imagine the future state of the maze to plan its moves. They even liken it to episodic future thinking in humans.
Like thinking ahead.
Yeah. And get this, there was this striking emergent behavior. Even when they looked at its internal processes beyond the number of steps it was trained for, the CTM just kept tracing out the rest of the correct path.
Whoa, so it wasn't just memorizing the training paths.
It strongly suggests it learned a general procedure for solving mazes. And proof of that, it generalized to much bigger mazes, 99 by 99, even though it only trained on 39 by 39 ones.
That's incredible. Learning the how, not just the what. Okay, so it can reason spatially. What about trust? Can we trust its answers? You mentioned calibration.
Right, calibration is huge. How much can you trust the confidence level an AI gives you? On ImageNet classification, the CTM showed very good calibration.
Meaning if it says it's 90% sure, it's probably right about 90% of the time.
Exactly, which makes its predictions much more trustworthy for us users. But the really wild part was CIFAR 10.
Go on.
On CIFAR 10, it showed better calibration than humans.
Better than us.
Better than humans tested on the same task. Think about that. An AI whose confidence is potentially more reliable than our own.
That's quite something. How does that even happen? Usually calibration needs extra tweaking, right?
It does. They called it an unexpected capability. It seems like the internal thought process, the way it refines its answer over those internal ticks, just naturally leads to better calibrated probabilities.
And internally, what's going on? You mentioned complex patterns earlier.
Yeah, looking at its attention on ImageNet, it's not simple. It shifts smoothly from region to region, sometimes zooming in on key features, other times looking broadly, even moving in specific directions across the image.
Like it's scanning and focusing.
Exactly. And another mind-blowing emergent thing, they observed low-frequency traveling waves in its neural activity.
Traveling waves, like actual brain waves.
Analogous to ones seen in real cortical dynamics, and the CTM generates these spontaneously without any explicit driving signal.
Just from the architecture.
Just from adopting these biologically inspired principles, it suggests these complex dynamics might be a natural consequence of this kind of timed, synchronized processing.
Wow. Okay. So adaptable, spatial reasoning, trustworthy, brain-like waves. What about pure logic? Like following algorithms, sorting numbers, that kind of thing.
They tested that too. For sorting 30 numbers, the CTM showed clear patterns in its wait times, how many internal ticks it took before outputting the next number. And these wait times correlated with the difference between the numbers. It suggests it wasn't just guessing, it was running some kind of internal sorting algorithm.
It figured out a process.
Seems like it. And for a parity task, figuring out odds or evens in a binary sequence, giving the CTM more thinking time, more internal ticks, directly improved its accuracy. LSTMs really struggled with that.
So more time helps it think through the algorithm.
Yes, and it even showed evidence of a kind of reverse search through the data sometimes, suggesting a form of planning.
Fascinating. Okay, one more area. Memory and interaction. How does it handle remembering things over time or dealing with a changing environment?
They did a Q&A task with MNIST digits. It had to look at digits, remember them, and then do math based on instructions given later.
Right.
And it performed strongly even when the digits it needed to recall were technically outside of the memory window of the input sequence.
So it held on to them internally.
It suggests it learned to memorize and recall purely via the organization and synchronization of neurons, not just storing data, but encoding it in its dynamics, like a real memory trace.
That's much more organic. And in reinforcement learning, like game playing.
Yeah, things like cart pole or mini grid. It could interact continuously with the environment and achieved similar performance to standard LSTMs in partially observable settings, where it doesn't see everything at once.
Okay, so competent there.
Competent, yes, but the key difference was inside. The CTM showed richer neuron dynamics while doing it, again suggesting a more complex internal process even when the final behavior looked similar.
Okay, so stepping back from all these specific examples, what's the big picture here? We've seen the CTM adapt, reason, calibrate itself, even show brain-like waves. What does this all mean for AI?
I think it really demonstrates that explicitly modeling time and synchronization isn't just a theoretical exercise. It leads to tangible, emergent benefits. A whole new set of capabilities seem to just appear.
And this idea of synchronization as the representation, what are the advantages there?
It's incredibly flexible. It can capture info at different levels of detail, any number of resolutions. It acts like a form of memory, more like an experience than static data. There's also potential for things like plasticity, maybe even learning without gradients, which is a huge research area. And technically, it's a high cardinality representation. It can pack a lot of diverse information, which is great for handling multiple types of data, like vision and language together.
Right, the multimodal challenge. Now, this work is inspired by biology, but you noted it's often trained on kind of unnatural data inputs treated as separate things. Where do they see this going?
Yeah, the next big leap is training CTMs in continuous worlds on data that flows, like video or text read in order, because that's how the real world operates, right?
Absolutely.
Imagine a CTM reading text. It could potentially build this evolving contextualized world model of the narrative without needing the usual tricks like positional encodings that current models rely on.
Because the timing and synchrony handle the order inherently.
That seems to be the idea. They found that just trying to use snapshot representations didn't work well when they moved towards these dynamics. Synchronization, being fundamentally about relationships over time, was the elegant solution.
An AI that builds its own evolving internal model of what it's seeing or reading, that's powerful vision. But are there downsides? Practical challenges? It sounds computationally intensive.
There are definitely trade-offs. The big one is that this sequential internal thinking process cannot be parallelized like standard deep learning.
Ah, so slower training.
Yes, potentially significantly longer training times. And there's additional parameter costs for those little models inside each neuron.
Okay, so it's not a free lunch.
Not at all. But the researchers argue the utility can be high. The unique capabilities might be worth the extra cost and time. Their philosophy seems to be about borrowing concepts from biology, strategically, not necessarily building a perfect replica, to unlock capabilities currently missing in AI.
Makes sense. Borrow the good ideas, don't get bogged down in exact mimicry.
Precisely.
So we've taken this deep dive into the continuous thought machine. It really feels like a fascinating step, doesn't it? Trying to bridge that gap between raw computing power and the way biological brains seem to work.
It's definitely a compelling direction.
And that core idea, weaving timing and synchrony back in, leading to adaptive compute, amazing calibration, this different kind of internal process, this powerful stuff.
It really opens up new possibilities.
The thought that AI could develop emergent properties, like those traveling waves, just by adopting a more brain-like architecture, that's honestly captivating.
It suggests there are fundamental principles of intelligence we might tap into by looking more closely at nature.
So here's something to think about as we wrap up. Imagine AI like the CTM, where the thinking itself unfolds over time through these rich dynamics. Could that lead to systems that don't just give us an answer, but can actually show us how they got there? A truly interpretable AI.
That's the dream for many researchers, isn't it? Transparency through dynamic process.
How might things change if AI could genuinely learn and adapt its thought processes, the way it approaches problems, much like we do? That feels like a whole new level of intelligence. Anyway, the deep dive is all about giving you the insights to explore these frontiers.
Hopefully sparking some new thoughts.
Exactly. Food for thought on the future of thinking machines.